Right now, every single time we want to leave the Earth, we have to start a massive, highly controlled explosion. If you look at this cross-section of a rocket, you can see a strange paradox in physics known as the rocket equation. To lift a payload, you need heavy fuel, but to lift that extra weight, you need even more fuel. As a result, 90% of the entire vehicle is just sloshing, highly explosive liquid. Only a tiny sliver at the very top makes it to space. Because of this massive weight penalty, sending a single kilogram of anything into space, whether it is water, a complex communication satellite, or even a human being, costs tens of thousands of dollars to achieve. We are essentially riding giant controlled bombs into the sky, which guarantees that space travel remains incredibly expensive and closed off to the general public. For thousands of years, humans have dealt with gravity in exactly one way, by stacking materials from the ground up. We started with massive, wide bases made of heavy stone just to get a little bit of height. Today, with advanced steel and concrete, we've stretched that exact same idea into the clouds. But there is a strict mathematical limit to this. If you keep stacking a structure infinitely upward, the immense gravitational weight of the materials will eventually crush the lower levels. So, if we want to reach space, we have to flip the blueprint. We can't build up from the dirt. We have to hang our structure down from the sky. Take a look at this diagram of a hand spinning a rock on a string. As the hand spins, the rock wants to fly away. That outward pull creates tension, keeping the string perfectly straight and rigid. Now, let's swap out the hand for the Earth, and the rock for a massive space station counterweight. As the Earth spins, centrifugal force tries to fling that station into deep space, which pulls the tether completely taut against Earth's gravity. Here's the trick, though. If your space station is moving faster or slower than the ground below it, the cable will drag across the planet and destroy everything in its path. So at what specific altitude do we need to place our anchor so it stays perfectly above one spot? As we can see in this animation of Earth's orbital rings, the answer is geostationary orbit. At exactly 35,786 kilometers above the equator, the orbital speed matches Earth's daily rotation perfectly. Because the station is totally synced with the planet's spin, it hovers over one exact spot, giving us a stable, permanent anchor point to drop our highway down. But hanging a cable down through 35,000 kilometers of space introduces a massive physical hurdle, the cable's own tremendous weight. Gravity pulls down on that much mass so aggressively that standard materials would rip themselves apart. Even the strongest industrial steel cable would snap under the tension of hanging that far. To survive this, we need a material with massive strength compared to its own weight. We need carbon nanotubes. Here, we see a microscopic view of a carbon nanotube lattice. Unlike rigid metals, these atomic structures are incredibly light, and they stretch perfectly without breaking when massive pulling forces are applied. We can already grow these inside laboratories. Once we figure out how to weave them into a continuous, miles-long tether, the math proves this structure will hold. Once the tether is successfully hanging, it faces its next major threat. Low Earth orbit is a dense junkyard. Millions of pieces of dead satellites and broken metal are circling the planet at 28,000 kilometers per hour. A strike from a single rogue bolt traveling at that speed hits with the kinetic force of a bomb. If the space elevator is built like a rigid pole, a collision would shatter it. The solution is to build the tether as a flexible ribbon and anchor it to a mobile base out in the ocean. In this schematic, the ocean platform moves horizontally. When radar spots incoming debris, the base drives a few miles aside. This sends a ripple straight up the massive tether, gracefully bending it out of the way of the collision. With the anchor stabilized, the materials woven, and the debris dodged, the cost of going to space drops from thousands of dollars per kilogram to just a few dollars. This technology finally breaks our reliance on explosives, turning the solar system into a routine destination for all of humanity.